right, good morning. How you guys doing? The class just before this? What class is that? Okay. Climatology? Okay. How was
It's a 4,000
difficult?
level course. We've never had a big rec for it, so we don't know anything.
Everybody else in the class is like, oh, and then like whole things on top of it now, and then we just like look at each other like.
I think I got a P.
Gotcha.
Not too pleased.
Is that in the environmental science department or geography? Okay, gotcha. Yeah. sounds a little bit like the type of stuff my undergrad was slightly related to that. Yeah. So I can appreciate that. I kind of did the inverse. I took a few environmental engineering classes and was like, well, this is similar, but wait, what are we doing? All right. So today we're going to resume talking about titrations a bit. Didn't quite finish what I wanted to get to, and probably what you needed to do like a perfect job on the homework, but hopefully you had enough to get you started to draw some sort of curve. I think taking the Excel approach is probably a good idea. There's also a couple ways, had we gotten there, we could kind of sketch it out by hand. I'll like I said, I'm going to be lenient on that and see kind of what you did and go from there. So talk a little bit more about titration today, and then we will switch over and discuss the homework solutions, go through those, answer any questions you might have, and go from there. All right, so last time we talked about titrations, and we said, well, there's a couple limiting cases we could take a look at that would simplify our calculation for what is this CB minus CA. And I wanted to move on from there, and we kind of looked at this graph a little bit, just describing the basics of, all right, how much base are we adding? Or on the inverse, how much acid have we added if we're going the other way, right? We can titrate it either way. We just, by convention, we approach it as if we're adding a base and we're going to be moving then upwards on this, on the y-axis, and then from left to right, of course, on the x-axis. But of course, we could select an acid and add a strong acid to something instead and do that in reverse. Okay, so there's a couple of terms that I mentioned and I didn't give much, hadn't quite gotten there last lecture, and that is the F and the G. So we see two additional axes here we could take a look at for the x-axis. And what these are providing is really some fraction of the total amount of base or acid that we would have to add in order to get from one equivalence point to the next. So when we say F is 0, that means we're starting at the HA equivalence point. And if you recall, the HA equivalence point is to say that how many protons, how much acid would we have to add to a system to yield HA given some concentration of A if we had not added it in the form of HA, if we had added it all in NaA, for example. So if we had a bunch of A minus without any connected acidity, how much acid do we have to add to get that all the way to the point where it's HA is the same amount as the H plus in solution? We drew up the graph that said, okay, here's the H plus concentration, and we could track and follow the line of HA, and where those two crossed, that was our equivalence point. So the whole equivalence point deal is quite important, and it shows up here in these titration curves as essentially these inflection points. And it's a very handy way to know when does this molecule, when does this acid begin having a big impact or stop having a big impact on our pH adjustments. So the F then would be the fraction of progress towards reaching NAA. If we started almost like a race, we start at the HA equivalence point, and we're going on our way to the NAA equivalence point, which is a more basic condition, then halfway there should be F equals 0.5. So if this is all F, then this would be 0, 0.5, and once we reach that, that would be 1. Right? So that's what F is describing. We can go past the equivalence points. There's no problem doing that, or we could go negative. And so that's what we see here on the bottom x-axis for F. We see a 0 starting point here. These are the equivalence points for the two. This is the equivalence point at least for this curve, right? So to say it starts at pH 3 and we're going to the right. Okay, then we can find the next F equals 1 here. This is the NAA equivalence point. And I think this is, yeah, these are equivalence points for both of these systems. So at that point we see when we've reached there, that NAA equivalence point for that particular species. So we can kind of see graphically where that's arriving. Okay, G is very similar. It's essentially the inverse. If we are adding acid, what fraction of acid have we added to progress ourselves from the NAA equivalence point to the HA equivalence point. So in this case, for G, we are going from NAA to HA equivalence points. And we could look at that in the same manner. Of course, that's going to be kind of flipped on our pH diagram, right? That's going to be the lower the pH, the more progress we were making towards HA equivalence point. Okay, we can also describe these mathematically. F could be described as that amount of strong base, that's the Cb minus Ca, divided by the total acid. And you can see this will become 1 when the amount of base we have added is equal to the total amount of acid there. Right, so it kind of becomes a bit intuitive if we stop and think about it that way. Another way we can write this, we can get Cb minus Ca in terms of the fraction of acid there. So A1, alpha 1, excuse me, that's the fraction that is A minus, right, for an HA system, times the total amount of acid. So that gives us essentially here the concentration of A minus plus OH minus minus H plus, all that over the total amount of acid. That component right there is where we have the limiting cases where we can essentially simplify in some cases, because sometimes A minus is almost negligible the whole way through. So in a very weak acid, most everything is going to be in the HA form for a lot of pH ranges, and so it never really shows up in relevance to that role of the OH minus and the H plus. So in some cases, that term kind of goes away. We can always leave it there, and it will just won't make much of an impact. And that's why we see for these graphs, last time we were looking, okay, this is case 1, this is case 2. In the case where A minus is not showing up much, that means it's almost all driven by the pH of the system, whatever base adjustment we're doing, titration, that's kind of the only thing happening. And so it's a very simple curve. When we have it showing up, it's going to shift. It's essentially demanding some protons or some Yeah, so the A minus will be demanding some protons and taking some of them up and shifting everything a bit to where we need to add, it changes the amount we have to add for the base. Okay, we can also look at the math for G. It would be essentially 1 minus, I think it's almost, maybe it is exactly 1 minus F. And we can rearrange it in this way. We could put it in terms of alpha 0 if we wanted as well. Okay, just a little more elaboration here, kind of showing it. We can essentially use these to get 3 different axes, right? We can put 3 different x-axes at least. We could also put the strong base acid. We could put that in, the strong base added. We could put this into volume terms instead if we wanted to, or this concentration, equivalents per liter. Either one's possible, and if we go to the volume, maybe that makes it a little more practical so we can relate exactly what we did in the lab to what's going on here. Okay, so we have a few things like that. If we wanted to account for the amount of volume we're adding, so when we do the titration, we are adding some volume to the liquid that's going to dilute it. It's typically we're adding, point something milliliters, and we're going to do this in a fairly large volume, maybe half a liter or something. So typically, this dilution factor is something like 1/1,000,000th. So it's not like we are changing a lot, but we can certainly account for it. There is a whole page discussion to it, box 7.1 in our book. If you did have some interest in seeing all those derivations, and they kind of start here saying, well, initially we have some amount of acid in the initial volume. That's going to be the total amount of acid in the new volume. Like that's going to be the mass balance. So if we know a new volume, we haven't changed the amount of acid, we just have diluted it. So we can put that mass balance together to solve the effective new concentration of the acid. We haven't created or destroyed any acid, we just put it on with a larger volume, right? And so another way we might write that is solve for AT here and get the initial amount, initial concentration times the initial volume divided by the new total volume. Okay, and we can then elaborate that into any time we are, so we can take this, and any time we're using AT, we can fill that in there. It makes the equation slightly more complicated, but we can substitute it and deal with it that way. And likewise here. So just highlighting that we can do that. So we'll just say maybe a little less messy. Okay. So a couple other points about the F and the G. As we plot them and as we take a look at titration curves or draw them, there's going to be 3 points that are pretty good to highlight. And usually these will correspond with what we'll talk about in a couple minutes with the inflection point. So when F is 0, we know we are at the HA equivalence point. That means that we've, by definition, added no net base. That's kind of how we define it, is the CB minus CA is 0. When we are at F0, that's when we're at that HA equivalence point. F being 0.5, I think we always find an inflection point there. We'll talk about that and look at that in a moment. I think that's the one that's guaranteed. We often find an inflection point at F equals 0 and F equals 1. Those are not guaranteed, as far as I understand. But it's going to be also the spot where we have a very, very rapid change in our pH per change in our added base. So if we take a look back at the graphs here. Okay, maybe I'm wrong about that. So discount that. Let's see. F.5. Okay. Okay, scratch that. But it's going to be that halfway point. It's fairly relevant. We know that we're added half of the amount of base we need to get from the HA to the NaA equivalence points. Okay, then Fu equals 1, of course, is when our Cb minus Ca, the amount of base that we've added, is equal to the amount of acid that we have total. That gets us to the NaA equivalence point. And again, we can calculate that Cb minus Ca according to these. Subject to simplification if we decide to, but that's just a matter of do we have a weak acid, extremely weak acid, or extremely strong acid. Kind of changes a little bit of how we handle this stuff. But we don't have to simplify, we can just put it in and go. Okay, so the book provides us an example. I'm just going to walk through it with you to essentially create or calculate a titration curve. And here we can kind of step through this. It says we are assigned to calculate the detailed titration curve for F equals 0 to 2. So that just gave us the x-axis range as pH versus F, with HA is acetic acid, the pKa of 4.76, an initial volume of 0.025 liters, total acid concentration of 10 to the minus third molar, using a basic titrant concentration of 0.1 normal NaOH. We're going to neglect dilution and neglect activity, assume 25 Celsius. And then it tasks us to generate 3 different versions of an x-axis. So one would be the volume added, volume of our titrant. One is going to be the Cb minus Ca in equivalents per liter, and one is going to be F. And of course, F is what we're going to scale from 0 to 2. Okay, so the way we're going to approach this then is to get pH as a function of the different x-axis, right? Y is a function of x kind of situation. pH is our y-axis. We know that our graph will look something like this. And then we need to put that in 3 different terms for x being the F, the strong base added, and that volume of the strong base added. So volume of the titrant. Okay, so at this point we can do a couple simple things. And first of all, we could calculate where are we starting? What pH do we need to start on the y-axis? And we can find the value where F is 0, put in 0 here, and then later we can put in 2 and figure out what's the value of our system, or what are our what's our range here. Okay, so essentially when F is 0, we can solve that, and that's pH of 3.91. Let's see. Okay, then we get from box 7.3. I think that's what I was. No, not that one. Okay, this is calculating, and I think I have it next actually. A little bit. This is just calculating the volume we're adding. So what we're going to do here is say, what volume of titrant are we adding? Well, we can multiply the concentration of our base. So Cb here, this is our NaOH concentration. The VT, that's the volume we are adding, and we're dividing by 10 to the 6 because we are dealing in microliters, so we're converting that to liters. We're going to divide all of that by the initial concentration of our acid times the initial volume of the solution, also in liters. So that's going to give us eventually that ratio, right? That a ratio of concentration of our base to concentration of the acid. Let's see, is that right? No, concentration, and we're multiplying that by a volume. So that's going to give us a mass or moles of base, and then per moles of acid. That's what it'll give us. Okay, we're setting that equal to, that'll be our F, and we can set it equal to this stuff here. So that's kind of how we're getting there. Okay, it goes on, calculates that, or essentially getting the H term by itself is I think what we're after. So doing some simplification, or getting rather V as a function of everything else. Yeah, V, the volume of the titrant as a function of H plus. So we see here, at this point we can insert the Ka over H plus for our alpha fraction here. Plus Ka times that At. So sorry, that's all of this would be the alpha fraction times the At times initial volume. And then again, we're going to get the OH minus in terms of H plus instead. So we're going to use the equilibrium constant for water. So essentially we get all of this in terms of get V, this volume of the titrant, in terms of H plus. So I suppose we could do it in reverse and get H plus in terms of this X value, but it doesn't actually matter too much. We can set it up in Excel either way. And then putting this in here, we are starting at that 3.91. If we solve for the, where F equals 2, I think we can find the pH there. It would end up being somewhere just after 10. Let me fix something real quick. Okay. Oh, that's just okay. All right. So we can see then kind of how we are, how we're going about plotting that. And let's see. Yeah, we can calculate the volume added. We can calculate F for any given pH. And of course, we can also calculate that Cb minus Ca accordingly. So it's really a matter of setting it up with these equations in place to do the calculations and then plotting that. Okay, does that make some sense? I know you guys didn't have to do the volume, but did you do this in Excel for the homework problem for 3? Did you set up a pH versus anything, or did you just sketch it? You just sketched it. Okay. So when we go over that, I'll show you kind of what it was looking like as I was setting it up in Excel. Didn't quite go this far with the volume, but you know, you could do that. Is kind of the point. Okay. So. There we go. All right, so here's just a little bit further about accounting for that dilution if we wanted to, if we felt like we needed to. This is all, I think that's box 3 that the book was referencing. And we know we can do that math. It's just about elaborating it. We can put Cb minus Ca in those same terms, just as we kind of saw we were starting to do with the acid. It's just a volume correction. So there's nothing particularly difficult about it. It's just taking that volume correction and adding it to the different equations we've been using. So if you wanted to see more, there's certainly a little bit more of an explanation, but here's kind of the basics of that. Okay, so I mentioned inflection points. Would like to highlight that now. When we are assembling a titration curve and taking a look at a titration curve, these inflection points can tell us a lot. And so we can learn about our system by finding and identifying them. And it's a way we can draw our titration curves as well. If we can calculate the inflection points, then we can set up the drawing accordingly by drawing a curve such that we go from concave one way to concave the other way at those points. Right? That's what I'm referring to as an inflection point. Now, I mentioned this already, but typically we have inflection points that are approximately f equals 0, f equals 0.5, and f equals 1. So we have 4 different conditions here. We see this is drawn with f, and so f from, I guess, -1 to 2. And if we just hone in on this 0 to 1 range, we can notice that for each of these curves where we're crossing this HA equivalence point, so f equals 0, that is the moment where we are going from kind of an upward slanting over to this one. Now this first one at pKa3 is not necessarily inflecting, right? That doesn't look to me like it's inflecting because it just looks like it's raising the whole time. So instead, that one has an inflection point over at f equals 1, which corrects my earlier thought that maybe at 0.5 is where it always is. In fact, at pH 11, that one also looks like it, or excuse me, the pKa 11, that also looks like it does not have an inflection point here or here. I think the only inflection point would be where that crosses the HA equivalence point. So, so maybe it can either have all 3 or one of the edge cases, maybe. At any rate, those are the 3 that we can have for a monoproduct system, and we can see that pretty reliably we will often have one here in the middle at f equals 0.5, f equals 0, and f equals 1. So that's something we can do is calculate, and anytime we can find a low and a high inflection point, then those are going to be our equivalence points approximately. Maybe 0.001 off or something like that. But essentially, they should be exactly the inflection points should be the equivalent points if we have these 3 and we can identify the low and the high one, right? So if we just have one inflection point, I think that means it could be let's say HA or NAA equivalence point. So if we just have one inflection point on a graph, we can't necessarily say too much about that unless we see a little more context. If we plot it against f, of course, then we know. But okay, so we can use these inflection points as landmarks. We can then perhaps do some clever math or simplifications to say, oh, okay, here's then our equivalence point, given that I know how this thing is curving. Okay, so they are kind of landmarks in that sense, and this is essentially coming from that, these shapes are coming largely from the alpha fraction. So if we recall the function, because what we're plotting is how the pH changes when we change how much base that we're adding, right, or acid. And so when we think about it in that regard, that calculation for CB minus CA had something to do with the alpha fraction, alpha 1 in particular. If we do it in reverse and we're using the G factor, of course we are adding acid, we can use the alpha 0 fraction, that would maybe be simpler that way. You can always, if you know one of those, you know the other and you can relate them. But if we take a look at how those change as a function of pH, these alpha fractions, we notice that for, let's say, a pKa of 7, the alpha 1 is relevant for half the pH scale, right? But for pKa 3, the alpha 1 is relevant for almost the whole pH range. And so if that's the case, that kind of shapes at what point is our adding the base having an impact. Because the alpha 1 fraction, this is like saying most of it's A minus, whereas alpha 0 would be most of its HA. So if we add a base to HA, we are prone to pull off the H plus to satisfy it. But if we add a base to A minus, it doesn't really care too much. There's not a whole lot that's happening, right? And so when we, or there's not that buffering kind of occurrence. So if we take a look then at our how pH is changing as we're adding acid for this pKa3, it's kind of flat and not so interesting for this range of F, which that could be, if we take a look, that's pH starts at 3 and goes up. So if we look at over here at pH 3 and going up, that's around the time where the alpha 1 fraction, if we, on this one, right, pKa 3, we are already 60% A minus. So it's under that range of pHs that would take us from the equivalent point, the HA equivalence point onward. It's really pretty boring, right? There's not a lot that's happening. It's already almost all A minus. So we're not having some interesting buffering transition on that curve. So that's why we see essentially not much action here. And I think we could probably expect the inverse if we had a really, really high pKa value, and it would be kind of in reverse this way, where not much happened under the relevant scale. So I think that the same exact thing can hold true if we push it to the other extreme, and we don't, in our relevant scenario never gets us down to like pH 3 range or something. Okay. So I think that's about what I wanted to say on this. Does that make some sense? We can still kind of see these inflections happening or not happening in some cases accordingly. All right, a few notes. I'm not going to go this far into depth on these pieces, but you could, and maybe we'll revisit a little bit of this later. If anything, probably the polyprotic acid systems. Couple things just to note: you can draw these by hand, especially once you know these. And so we could take a look at this template here. We could draw something with concave up during this region until we land on something. And I guess I'm just passed through that one, so might as well. And then we're going to kind of flatten out or start concaving the other way at least. Go through that one. Let's see. I'll try to do this a little better. So if we were concave up and then it stops going concave up, or maybe it's not, maybe it doesn't stop. And then this is concave down, something like that. So I don't know if I'm drawing that particularly well, but we could imagine drawing those well and getting those concave pieces correct and do that by hand. And you could then do that by calculating. We had that equation for F equals blah, 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 blah. Set F equal to 0, set F equal to 0.5, set F equal to 1, and then draw accordingly, right? Okay. Following that line of logic, if we have a graph like that, we can take the first derivative and find those transitions very easily. When we're taking a look at the concave aspects, essentially what we're doing is we're saying, oh, we just went from an acceleration, so to speak, to a deceleration, right? And taking the derivative is going to find that for us, that rate of change, very easily. There's also another concept of approaching titration, the Gran functions, or Gran titration functions, and these are there's a fair amount of information there, so I'm just going to leave it at this for now, unless really feel like we have to go there or need to come back to it. But essentially, it's an assumption that, well, mostly this is, when we're adding the strong base, it's kind of like graphing it versus OH minus. So in some scenarios that's relevant, or with some caveats, we can do essentially the same thing and plot this versus OH minus in a way, versus that volume of titrant. So that's something that can also be looked at for your curiosity if you want to go there. I think those are one way we can approach a polyproduct system. So if we have, instead of an HA system, let's say a H2B system, where we're going to have many more inflection points and more activity in terms of where things are happening, certainly something that we can get into. I don't have it written here, but there's also some discussion, at least in some of the books, and this might be later in this particular book, but when we take a look at buffers and how they are working, we can calculate a buffer intensity, and kind of look at the buffering capacity. I think we're going to touch on some of that as we get to the carbonate system anyway. Okay, so there's a bit more that we could go into, but I feel like this is good enough for the moment, and we kind of need to move on. So any questions on that stuff before we get to the homework? All right. Okay, so the first problem, we had hydrofluoric acid, HF. It's a weak acid in water, but we don't want to underestimate its danger. It's not weak in the sense of what it can do, right? Weak in the sense of it stays as HF for a range of pHs in water. If you didn't know, it's quite toxic, and it will etch or dissolve glass. So if you ever had to work with it in a lab, you don't use glassware, you use plasticware, because it looks and smells, and I don't know about taste, but maybe tastes just like water. So it's one of the reasons, the main reasons why labeling even your DI water is really, really critical. If you had a unknown vial of clear liquid in a lab that uses HF, you kind of have to assume that could be HF, which is, who knows, it's used fairly often. So it's, especially material science sort of labs, at some point you want to be really meticulous with that kind of stuff to label the DI water, even if you just filled it for a minute and you're going to dump it out again. So I'm just going to continue my tangent for just a moment longer. It's really dangerous, and the thing is, it will pass through your skin pretty easily, and it's really, really reactive with calcium. Now, you might think that the danger is, I don't want my bones to be dissolving when it reacts with that, which can and would happen. But the real danger is it's going to react with the calcium in your bloodstream, and calcium is mandatory in your bloodstream to allow your nerves to signal, particularly for your heart. So you'll get a heart attack and die pretty quick if you had a large HF exposure without taking quick action. The quick action, thankfully, is you take essentially what's toothpaste with a bunch of calcium carbonate, if you had a splash and you knew it, and coat the thing really thoroughly. You wash it off real quick first, and then you do that. So there are preventative measures to be taken, but it's no joke to work with HF. I've received some training, but I've thankfully never had to work with it myself. Okay. Anyhow, HCl is a strong acid. It's a little more relatable with stomach acid. The acidity constant for HF is 10 to the minus third m, while that of HCl, that's HF, while HCl is 10 to the 8th. So the question says, assess the driving force for these respective acid strengths using the following thermodynamic data for 25 Celsius. Okay, so when we're talking about the driving force, this is largely delta G, right? We're really wanting to know delta G, but we can also discuss other factors about the entire equation where if delta G is telling us whether or not it's going to be spontaneous to occur, we remember that's also dealing with the enthalpy and the entropy term, which would be T, so this would be change in H, right? Plus T times change in entropy. So there's a couple things that are at play here then that we can kind of look at. And if the enthalpy is negative, that means it will give off energy when it reacts. So you can think of a solution heating up as the reaction happens. Some will actually take energy away. If you think of, we could have a hot pack that, supposed to keep your toes warm or something. You break it open and you have a exothermic reaction happening. We know it's also favorable because the reaction's happening. But in reverse, you could also have something that's pulling energy out of solution, and it has a positive enthalpy, so it's going to consume some energy. That's also possible. Okay, then we have the entropy term, and this is, how ordered, what's the change in the ordering of the solution or the system. If you have something crystallizing, you're becoming more ordered. If you're having something dissolve from a crystal, you're having more disorder, and it's favorable to go towards higher entropy, right? So all that to say, we can then do some calculations here and kind of look at, it's not exactly this topic that we discussed a bit, but it's kind of along these lines, right? So we can at least calculate these terms. We'll say delta G for HF and delta G for HCl, and take a look at each of those. So, in fact, we're given the delta G naught, right? So we can, why don't I do this? I'm going to write up for each of these minus. Oops. Okay, so we know that this is kind of what we can write for each of them. And so what I want to do then is to say, let's take a look at these numbers, keep it kind of simple, and just assess what's going on for each of them. So for HF, we're given, this is 16 kilojoules per mole. And on the right side, we have negative 13 kilojoules per mole. We already have enough information to find the T delta S term, so we don't actually have to do anything too complicated just to set it up this way and look at it, right? Because we have one equation, one unknown, so we know that, if we take 13 and add it to 16, that gives us 29 remaining, right, if we were to have solved that. So we can say this is also, so that's 29 kilojoules per mole. Okay, so with that, we can then stop and think about it and say, okay, well, the delta G itself, this is a delta G naught, so this is just at standard state. At that point, that's a positive. So standard state not necessarily going to do this dissociation reaction. But it would be favorable in terms of the enthalpy, in terms of it would give off some energy. But there's some resistance here based on the entropy term. Now, if we change the temperature, that might change the equation. Yeah, 13 minus 29 is definitely not 16. Yeah. Minus a negative, so plus 29. So this entropy term, the fact that it's positive, is kind of some resistance to our to the activity. So because we have a positive change in entropy for this reaction, that's going to provide some resistance. Now, if we change the temperature, drop the temperature quite a bit, that term becomes pretty small. And so going away from standard state here, then we were calculating delta G, and the enthalpy stays the same. Eventually, that minus 13 will be bigger than the entropy term, and it would be favorable. Right? So we can imagine some cases just by changing the temperature that it would. But in general, the summary here is this is resisting the reaction, even though it's favorable in some way, in an enthalpy way. And that's kind of goes back to relating to this little chart here, right? So if our delta H is less than 0, then it can be spontaneous. Yeah, so remember this was a minus and negative, right? So I guess we could just write it that way. So if delta S is less than 0, which is true in our case, it's spontaneous at low temperatures when T delta S is small, right? So that's kind of the way to think about this. This guy here, the next one, HCl, we have negative 48 kilojoules per mole equals negative 59. And to get that to actually be equal, we have to subtract a negative 11 kilojoules per mole as that term. And since our change in entropy is favorable and our enthalpy is changeable, or is favorable, this is going to be favorable and spontaneous at all temperatures, right? So in sum here, we could say this is sometimes favorable, but we have some resistance based on that entropy. Okay, does that make sense? All right. Problem 2 says we have a geochemically important reaction, that is calcite, CaCO3 solid, plus carbon dioxide gas, plus water as a liquid. It's going to be in equilibrium with calcium 2 plus in aqueous phase and HCO3 minus aqueous. So first part of this says identify the 3 concentration scales involved in the standard states for the reaction species. So this is referring to the fact that we might have molal, so moles per kilogram. That's kind of typical for our concentration units. We might have mole fraction, and also pressure. So it would be the 3. So since we have a gas, let's start with the solid would, I think we would use molal. We're going to have the gas, which would mean we're going to have a pressure as a concentration scale. And then for water, we would use mole fraction. Okay, part B says calculate the standard free energy change and the enthalpy for the reaction at 25 Celsius and 1 atm. Okay, so standard free energy, that's going to be standard Gibbs free energy, the question here, and then also delta H naught. The two things we need. Now, I'm embarrassed to admit how long it took me to realize what was wrong with my calculations on this one, because I was working it and I knew I wasn't doing something correct. So the first key here is to recognize that when we have this reaction, this equation, we have to relate whatever we're going to do with this calculation next to the proper reaction, and we have to make sure that's set up correctly. So we take a look at this reaction, and if we look closely, we don't have a balanced equation, right? There's no charge balance on the right. We've got 2 plus and 1 minus, and we have two sources of essentially CO2 or /CO3 on the left and only one on the right. So it will balance if we add a 2 here. It'll be very frustrating if you have some idea of what you need to get and you don't notice that. Okay, so that's a first key, is to make sure you've got the balanced equation. CaCO3 solid plus CO2 gas plus H2O. We could put a 1 in front of each of those if we want. Yields 1 calcium and 2 bicarbonate. At this point, the calciums will balance, the carbons will balance, the oxygens will then balance, and then the hydrogens will also be in balance. Okay, but you need that 2 there. So in particular, we need that because when we go to solve the problem, the way we're going to do this is essentially take the sum of all the products minus the reactants. But we're going to take the Gibbs free energies from a lookup table for each of them times the number of moles partaking in that reaction. So if you leave that out, or if you did not have this part, your number will be quite off from what you might expect. And a lot of times in these reactions, we expect something like, I don't know, a lot of these energies, I mean, even if we just take the look above, right? We're somewhere in the range from 10 to 100 kilojoules per mole, right? So and if we miss that, we're something like 1,000. It's like, this doesn't feel right. Okay, so let's write this out then. It's mostly from the lookup tables. You take any book or the internet and essentially find it from there. But we'll say the delta G naught for formation as an equation would look like this. The sum for each species, I'm just going to say all of I, the moles of it times the delta G of formation for that particular species. Okay, and that would be for the products minus the same for the reactants. All right, does that make sense? And then we can actually the same thing is essentially true for delta H, or we could calculate it a little differently. Okay, so then we would take for the, let's see, do I have it written properly? I think I went ahead and did it in Excel, so I'm just going to pull that up to be very clear about that. Okay, so I went to the lookup tables and I grabbed all of the delta G's for formation for the reactants and the products. And I went ahead and got the enthalpy, and in case I needed it, the entropy as well. You'll note that a lot of the lookup tables will have entropy in joules, whereas the others would be in kilojoules. So make sure to note that if you needed it. for any of these problems. Okay, so then I set up the equation for delta G, where I was taking the products minus the reactants, right? Summing them, the right side of the equation summed, multiplied by each of their things minus the left side of the equation gets us a value of 33.2 kilojoules per mole. Okay, and then when we do the enthalpy, same process, essentially the same equation. If we really wanted to, we could probably instead plug in all the entropies and do it that way, solve for the entropy term, and then solve for delta H for the whole system given those two knowns. But there's no really reason to do it that way instead, as far as I'm concerned. So we do that and we'll get a negative 40.1. So I'll go ahead and just write these up. So this should be 33.21 kilojoules per mole and negative 40.1 kilojoules per mole. Okay. Does that make sense? Yeah.
So is there like a rule of thumb for the ranges for Gibbs energy and enthalpy?
Rule of thumb, what do you mean?
Like, should we know that this cannot exceed this value? Because I know I didn't balance this, so I had like 100.
Yeah, I mean, part of that's, I have access to the solutions, just not necessarily the solutions themselves, but the answers. So I knew in part, but it was feeling off to me. So I think with some experience, if you work a few more example problems, probably a rule of thumb, if it's thousands of kilojoules, that's quite energetic, or maybe in reverse, right? So there are probably highly explosive materials that have a very, very low, negative delta G, but I'd be surprised if it was much more than 1,000. So if you get, so the 1,000 number, maybe it kind of feels wrong, but maybe it's right, in my mind. But if it was 1 million, I'm thinking there's probably a unit conversion or something wrong, right? So maybe just getting a feel for it. Yeah. Okay, so then part C asks us to calculate the equilibrium constant. So we need to find K. And we've got several equations that kind of deal with K from a thermodynamic perspective, one of which is delta G is equal to RT natural log of Q over K, K over Q, excuse me. Now this is delta G not at the standard state, but what we can say is for an equilibrium reaction, the delta G is to say, okay, when we've gone through a reaction, we made some change. What is that difference in energy? Well, the difference in energy when we reach equilibrium is 0. That's kind of the definition of the equilibrium, right? So we can say at equilibrium, we know a couple things. We know that delta G is equal to 0, and we know that Q, which is our reaction quotient, all the pieces in Q have also, because we're at equilibrium, that goes to 1. Q is equal to K, and those terms together go to 1. Okay, so that means that's how we end up getting to the delta G at the standard condition is equal to negative RT ln of K. Something we talked about before. I'm skipping some of the derivation, but that's kind of the logic that gets us to that equation that we have. And so we can solve that. The book, if you want to, you can convert natural log to a log. It doesn't really matter too much to me, but a lot of people will report this equation doing just that to say, okay, log K is equal to negative delta G naught, standard Gibbs free energy, divided by 2.3 RT. The 2.3 is just converting log from natural log to log. Okay, so with that, we can then solve for K. Need to use the appropriate gas constant, or based on which gas constant we use will give us final results in final units in particular manner. And in this case, we can go with one that's going to yield 1.6 times 10 to the minus 6 for cubic meters per atmosphere. Of course, your number might vary a little bit if you used a different R and you have liters in atmospheres or something like that, and that would be acceptable in that sense. Of course, if you also had a different delta G naught, that would affect your answer, but this is kind of the approach that I'm looking for there. All right, then part D says, will an increase in temperature favor a shift towards products or reactants? And this is slightly more complicated than I was thinking it would be. And it's something that I probably should have covered but didn't. And that's the Van 't Hoff equation can be used for this. That's if we stop and think about these equilibrium equations, we recognize that K can be affected by temperature. Delta G can be affected by temperature. And so it's not intuitive just to think, oh, increase in temperature means X, right? It takes a little more than just simple intuition. And so I'm not, hopefully you kind of dug around a little and found this, but I'm not too worried if you didn't and you just gave me some logic that made good sense. So if we take a look at the change that occurs in K, so d ln K, per change in temperature, that's kind of what we would look for. So changing that equilibrium constant per change in temperature, is this a positive or a negative outcome is the deal. And that can then relate straight back into what we were just talking about up here. So we can find an equation. This is the Van 't Hoff equation that looks like this. That's delta H naught divided by RT squared. Now, if this is less than 0, then temperature, increasing temperature favors reactants. And that is true in our case. Okay, so that's the technical way to do it. Like I said, I know I didn't lecture on that. That's something that I'll add for next time. Any of you find the Van 't Hoff equation when you're doing this, or did you do some other comparison? Another way you probably could have done it was check on a particular K at 2 different temperatures. You could have tried 25 Celsius and then, okay, well, what about 30 Celsius, right? You increase the temperature, is this going to favor? Because once you find K, we know we can compare, do we have more reactants? Do we have more products? Which way is that pushing the equation, right? Okay. All right. So problem 3, we had hypochlorous acid, HOCl, has an acidity constant of 3 times 10 to the minus 8th at 25 Celsius. The strength of a sodium hypochlorite solution can be determined by titration with a strong acid. So this is essentially NaA. So we can determine that strength by titration with an acid. And so we're tasked to sketch a titration curve for a 10 to the minus third molar solution, indicating pH at the beginning and end point of the titration. So again, this is, we've now discussed this at a little more length for kind of what we might need. And you didn't really have all that information to start with. So I'll pull up my Excel sheet in a moment. We'll kind of talk a little bit more about that. But if nothing else, we ought to have had some sketch of pH versus the net strong base that we're adding, Cb minus Ca. In this case, we are doing a negative net strong base by adding a net strong acid. So perhaps, I mean, I think it would still make sense to write it this way. And then, you know, without any other information, we can just go from 0 to 14 as a pH scale, although I think we could probably narrow that down if we were giving more attention to, okay, what is the beginning and end point? How are we going to define that for this titration? I think that typically going a little above and a little below and beyond the F range of 0 to 1 would be good. So something like -1 to 2 for F is probably the range we ought to do now that I'm looking at it today, right? But I prepared most of my notes on the titration after solving this problem in Excel yesterday. So, so I'm a little backwards myself as well. So I think that if we were to do an alternate x-axis, I would say let's go from something like -1 to 2 for F. And that's going to correspond to some pH range. Okay, at any rate, we can then make our plot if we add in, so if we go to Excel and make a column of pH, a column for HOCl, well, we don't actually need the HOCl, but if you wanted to do a pH versus C diagram, you might do that, and OCl minus. But really what you'd want is Cb minus Ca. You could also add F at this point and or G. G might actually make a little more sense since we're titrating with the acid, but again, it's kind of inverted, so it's not a big deal whichever way. And then ultimately you're going to have something that looks curvy, right? You're going to have some curve. And it's probably going to be something a bit like that. And I think, you know, most of our titration curves are going to. So I'm going to move over to Excel and kind of explore that effort with you here. So I started, and just without even thinking too much about it, I was like, okay, what do I have? We'll do pH, we'll do, ended up adding H plus and OH minus at some point so that we could graph those, use those a little more conveniently. HOCl and OCl minus, we could make this curve. We've done that before. That's not what we're after, but it just, if nothing else, to kind of double check that things are looking appropriate, doesn't hurt to do that. I could have solved for the alpha fractions for every pH. That could have been worthwhile. Instead, I just put them into the equations themselves. I was using the this approximation here, the Cb minus Ca equals, and taking a 0 there. I don't know if that's, I think that is correct, that I can do that in this case, but I think if I go back to it, I'm probably going to just do the calculation without that approximation and just include the whole information because it's going to calculate it fine anyway. Okay, and then, okay, Cb minus Ca and F as well. All right, so what you notice is that pH 0, F is minus 1,000. So definitely way out of the realm of where we need to be in terms of doing something interesting. So if I were to, and here's the graph, by the way. And this is plotted at versus CB minus CA. We could also plot it versus F, and then cut that down to the appropriate range. And maybe I'll do that here in a moment, if we have time. Okay, so I just went ahead and took pH from 0 to 14 at 0.05 increments, just kind of arbitrarily. The book was suggesting something like that. And if we scroll down through the numbers for a moment, one thing we'll notice, you know what I'll do? On the last column is F. And as we get down to close to -1, we can start seeing, okay, here's where things get a little more interesting, and maybe we start our plotting from here. So pH 3, our F is at -1, and let's find where it's at 0. So keep going a little bit. It's approximately 0 right here at 5.3. And so that's going to be one of the pieces that we can highlight about, okay, when are we starting? What's happening here? Continue and find where it's 0.5. It's crossing the 0.5 threshold right about 7.5, which makes a lot of sense to me because the pKa of HOCl is 7.54 at standard temperature. So that's looking spot on in terms of what I would expect, where I would expect to see something to be relevant. We'll continue a little further and find where it reaches 1, and that's at 9.3, pH 9.3. So you could also just use the F calculation and calculate these, put in F is equal to 1, find your pH, F is equal to 0.5, find your pH, and so on. But we can also do it kind of graphically or just scanning through like that is the point. Okay. Okay, so that would give us kind of a way to identify certain spots. We recognized, we could look at F equals 0. pH at that point was 5.3. By the way, that also means G is equal to 1. So that's going to be our HA equivalence point. When F is equal to 0.5, pH was 7.5. G is also 0.5. That's actually the pKa. I think perhaps that always happens. Not 100% on sure of that, but that's notable at least. When F equals 1, pH was 9.3. Okay, if you, yeah.
So one is that you said we have alpha is equal to 1 for strong acids and then 0 for weak bases.
I said what?
I think it's just like 2 lectures ago, you said alpha was equal to 1 for strong acids and 0 for weak bases. That was the assumption we made to simplify the equation. So that weak acid and weak base, is it the one that is being titrated against, or the resultant acid or base?
When we're referring to that and making the simplification, we're talking about the acid that we're trying to study. So in this case, we're trying to study HOCl. We're going to study it by adding, in this case, a strong acid, probably HCl.
So it would be wrong to assume the alpha is equal to 1.
Are you saying, like, you're saying alpha, but do you mean alpha 0 or alpha 1? Okay, so the alpha 1 fraction, sorry, let me come back to my Excel sheet. Oh, I dropped it. I think it'll make more sense when I show it to you on Excel again, because we can see on Excel the other graph that I made is showing essentially alpha 1 versus alpha 2, 0, right, versus pH. So the orange one should be alpha 1 if I put it in alpha instead of concentration, right, the percentage of total. And the blue would be alpha 0. So in this case, we cannot assume that alpha 1 is 1 the whole time. So it depends a little bit. I think the safest thing to do, and what I'm going to do when I revise this, is not even make the assumption. But this should be an extremely weak acid because it does hang on to the proton for a long time. So I think this one is okay to use here. Okay, I'm going to move on a little quickly. So I think that's about all I needed to say there. Then we say, because HOCl is different from OCl minus, it's stronger, bactericidal. Disinfection is pH dependent, so it says sketch a curve representing how efficient the efficiency of disinfection depends on pH. So if we take pH versus some disinfection efficiency, at low pHs, it's pretty well efficient, and then somewhere around 7.5, it's going to be dropping to something like half. So it'll kind of look like a inverse of the thing. So something like that is what I would be looking for. Last one was actually quite simple. So this says benzoic acid as a pKa 4.2 can be used to inhibit biological growth. We've got some data showing the dependence on the minimum required toxic concentration for the pH of the solution. And we just need to interpret that to say, okay, which form of benzene, or not benzene, benzoic acid. So I'm going to write that, we'll say HBZ for the benzoic acid, and then BZ minus as, basically HA and A minus, right? We know that transition is at the pKa of 4.2, so that should be right here between, and we can see what's happening between that spot. Do we have more or less required? The less required to inhibit means the more hazardous it is for those bacteria, right, or whatever we're inhibiting. So that means that these guys are the stronger ones. That also means this should be in the range of HA, not A minus, because the higher the pH, we're deprotonating, and it's A minus. So the correct answer then is the benzoic acid. Okay. Last thing I'm going to say is, of course, we've got the exam coming. As you have experienced today and with this homework, I don't have a perfect grasp on how exactly I am teaching you, how well I'm teaching you these things. So just bear in mind, I'm going to do my best to make it appropriately challenging. I might mess up, and I'll take care of you guys if that happens. Okay? Or it might be too easy. Could also happen. What's that? I will probably give you equations if it's something simple. Maybe I'm not going to give it to you, and I'll probably give you. I will give you a lookup table, periodic table as needed. Yeah, I just haven't gotten quite that far yet. So. There's probably going to be some similarities. No Excel needed. No MATLAB needed. Yeah. Yeah. Okay. All right. Well, have a good weekend.